Hi everyone. So our next topic is center of mass, moment of inertia, and these are for plane regions, right? So regions in the xy plane here. So think of like a flat region R in the xy plane. The book calls these planar laminas, so very flat objects, right? So center of mass, moment of inertia. These are ideas that you'd encounter in a physics course or an engineering course. So why are we talking about that here? Because these are excellent examples for double integrals. So if you're wondering why do we need to calculate double integrals besides, calculating area and volume, um, here's more reasons why we need to do it, right? So here's more applications of double integrals. Um, but before we get to that, let's just get to the physics of it here, right? Before we even get to center of mass and moment of inertia, we need to talk a little bit about density. So the density of an object, as I'm sure most of you are familiar with, it's just the mass of the object divided by the volume of the object. Although here we're talking about plane regions, so there's no volume, so we divide by the area, right? So we can think of this as surface density rather than volume density. Okay. Right, and for a uniform object, right, you can calculate the mass, which I'll call m, by just multiplying density times area. Density times area, right? But this is only for a uniformly dense object, right? In other words, the density is just a constant. Right? If you look at most objects, right, whether they're in a plane, well, maybe not a plane object, that's kind of hard to come up with, but most objects that you look at are not uniformly dense, right? Some might be approximately uniformly dense, like a book. If you look at a book, all the pages are pretty much equal, right? So if all the pages are equal, then it's basically uniformly dense, right? But if you have a hardcover book, then the cover is going to be more dense than the pages, maybe slightly, right? Or possibly less dense, depending on the nature of the cover. So there's an example of an object that's not uniformly dense, right? Or if if you're reading this on a tablet or on a laptop, you just look at the laptop and they're not uniformly dense, right? They might be approximately uniform, but not exactly. In any event, yeah, so for a non-uniform object, if you want to calculate the mass, you have to integrate over the entire region, right? So the symbol we're going to use for density, I'm going to use sigma for density. And I know the book likes to use the Greek letter rho for density. But I prefer to use sigma. And, well, maybe it's not obvious why, but we've already used the letter rho. If you remember, the letter rho is just the distance from the origin, which has nothing to do with density. So I don't know why you would want to use the same letter for density and for distance. That said, though, the letter rho is a common symbol for volume density, right? That is the symbol that most books use. In your physics and engineering books, they'll use rho for density. So that's fine. And in most cases, it's not going to come into conflict with distance here. From the context of the problem, it's going to be clear, what rho represents, whether it's density or distance. But just to avoid all that, I'm going to use sigma. And in fact, sigma is the symbol for surface density. Surface density. And in fact, I think lambda is used for linear density if you just have, say, a wire density. a wire with different mass at different points, a non-uniform wire, right? Let's say it's more dense here than elsewhere, right? Then sigma is the common symbol for linear density, sigma for surface density, and then rho for volume density. But this book just uses rho for any density, and that's fine too. So again, be careful, because I like to use sigma for density. If you want to use rho like the book does, that's fine too. In any event, to calculate the mass of a non-uniform object, you have to integrate over the region the density. And the density could be a function of position, right? Density is a position of location. Right. So for example, in this object, in this region R up here, let's say it's more dense over here, right? And then it gets less dense as you move out over here, right? So it's more dense on the left than on the right, right? Non-uniform density, that's what we mean by that. So if you pick any point, right, any point in that region, you can, right, you can say, well, at that point, the density is very small, right? But if you pick a point over here, let's say, the density is a much bigger number. So density is a function of the point, the function of the position, right? That's the idea. And so when you integrate that function over the whole area, over the whole region, you get the mass, right? Right. And if density happens to be a constant, right, then when you integrate that constant over the area, it's just the constant sigma times the area A, which is exactly the formula we had earlier. But this formula only applies if density is a constant, okay? So now we can get to the formula for the center of mass. So once you're able to calculate mass, you want to find what's called the center of mass. And the center of mass is just a point. It's a location. So it's an x and a y coordinate. Again, for objects in a plane, if this were an object in space, you'd have a z coordinate as well. But remember, we use x and y to represent any generic point, right? If we want to talk specifically about the center of mass, this is a specific point. So for that, we're going to use the symbol x bar for the x coordinate of the center of mass and y bar for the y coordinate of the center of mass. Okay, and roughly speaking, that is a point. I'm running out of colors here, so I guess I'll go back to blue. So it is a point in the region, although it doesn't have to be in the region, right? But it's a point where if you were to balance that, right, that would be sort of a balance point, right? So think of the center of mass as your balance point. It's the point at which you could balance the object on your finger, right? So yeah, why is it towards the left? Because it's more dense there, right? If you have, let's say, just a uniform disk, say a circle, a uniform disk here, right? Then the center of mass would just be at the center of the circle, clearly, right? Right, so the center of a uniform object is just the center of mass. But let's say it's a non-uniform disk. Let's say it's more dense up here and less dense down here, right? So if it's more dense towards the top, if you want to balance the object, your center of mass would be closer to the top than to the bottom. Okay. All right, so how do we calculate the coordinates, right? Because the center of mass has an x coordinate and a y coordinate. How do we calculate those numbers? Well, they're also double integrals. So to calculate x bar, you're going to divide by the mass, so multiply by 1 over the mass m times the double integral over the region R of x times the density. So you have to multiply x times the density and then divide by the mass. At least this is how I remember it, right? This is my formula here. And then for the y coordinate of the center of mass, well, it's almost exactly the same thing. You still take 1 over m times the double integral over the region R, and now you just multiply by, or you take the double integral of y times the density. Okay. So again, these are the formulas on my formula sheet because I find them to be the most convenient, right? And the formula for mass is on there too as well. Right? So that's how you calculate m, right, in the center of mass formulas. And I realize our book does not adhere to that. Our book calculates x bar and y bar somewhat differently, right? It's the same formula, but they just use a different notation here. So for them, they calculate x bar as capital M, which is the first moment of mass in the y-axis, divided by little m, which is the mass. And then y bar is mx over m. So this capital Mx is sometimes called the first moment of mass, and it is going to be the double integral over r of y times the density. Okay, and my then is the double integral over r of x times the density. And if you find that kind of confusing, I don't blame you. In fact, I find it confusing too. I can never remember, look, x bar is ym over m, y bar is mx, and mx is the integral of y. I don't know. To me, this just seems really backwards, and it doesn't make sense to me. But if this is the way you do it, that's fine. You get the same answer, right? If you replace mx, right, in here, right, you get the integral of y times the density over m. It's the same formula, just expressed in a different way. So roughly speaking, right, when you have a point here, let's say it's just one point that you're revolving around the x-axis, right? So if the x-axis is the axis of revolution, right, the point just goes around the x-axis, right? But the distance from the x-axis is y. So you're multiplying that distance times the density. Okay, so that should explain a little bit where these formulas come from. That said, I'm really never going to talk about the first moment and x bar, y bar using these formulas. I just prefer not to bother with that. But again, if you do it that way, you get the same answer. It doesn't matter. I prefer to think of the formulas here on the left. Okay? So yeah, as a practical matter, if you want to calculate the center of mass, remember the center of mass is two numbers, right? It's x bar and y bar. It's a specific point in your region, right? So you have to calculate three double integrals. One for the mass itself, right? And then another one for x bar, and then another one for y bar. So as a practical matter, it's kind of a tedious calculation, but we will do an example later. Okay? But first, let's talk about moment of inertia. So for the moment of inertia, here's the basic physics idea. You have your object R in the xy plane. So it's a planar lamina, planar object. And we want to rotate it around, let's say, the x-axis this way, right? So you pick a point somewhere in the region, right? And you measure the distance from the x-axis, which of course is y. It's the y-coordinate, right? And because you're rotating it around the x-axis, it's going to be a function of the distance from the x-axis, right? So for the moment of inertia, we're going to use the symbol I for moment of inertia. That's the standard letter for moment of inertia. Subscript x, because that's the axis we're revolving around, the x-axis. This is going to be calculated as another double integral, right? But now you're multiplying y squared times the density. It's not just y, right? Remember, if it's y, that gives you the center of mass for the y-coordinate here, right? But here we're revolving around the x-axis, so we multiply by y squared times the density, and then we integrate that function, right? Right. And likewise, if you're revolving around the y-axis, then you measure the distance from the y-axis, which is x. You multiply by x squared times the density. Okay, so for that reason, these are sometimes called the second moments of mass rather than the first moments. I have not come across that phrase very often, but you know why it's second moment, because the exponent is 2 instead of 1. Right. Yeah, for the first moment, the exponents are 1s. Right. And there's also something called the polar moment of inertia. Polar. R. So this is if we're revolving around the origin, right? If we're rotating, say this way, either counterclockwise or clockwise, it doesn't matter, right? So now it's the distance from the origin. The distance from the origin is going to be, well, the square root of x squared plus y squared, right? However, we want the square of the distance. So the polar moment of inertia, we're going to use I0 for that, 0 for the origin. And it's going to be the integral of x squared plus y squared times the density. Oops. I squeeze that in too much. Yeah, times the density. Right? Or you can just integrate r squared, particularly if the density is a function of, say, r and theta, then that might be more useful there, right? And then the dA, of course, would be r dr d theta, so just be aware of that, right? Anyways, so those are the formulas for moment of inertia and the center of mass and the mass. All 6 of these are on your formula sheet here. So it's not like you have to remember any of these. And depending on who you're taking physics with, they may or may not make you memorize these. I never had to memorize these. I don't think so. But having used them many, many, many times, they kind of come second nature to me after a while. Anyways, right, so now we can get to an example where we actually calculate mass, center of mass, and moment of inertia. Oh, before we do that, there's something called the radius of gyration. This is in the book, but I'm never going to ask about it. And to be fair, I have never seen this in a physics book. So maybe it's an engineering concept, or maybe I just missed it, right? In my textbook, which was over 1,000 pages long in physics, I could have easily just missed it. But just to be complete about it, for the radius with the x-axis, so that's, I guess, the distance from the x-axis, it's just the square root of the y moment of inertia divided by m, and then y double bar is the x moment of inertia divided by m. So if you see this in the homework and they ask about the radius of gyration, you can safely ignore it, or you could do it, for just because you're curious. If you want extra work to do, that's fine. But it's really not something I'm going to ask on a test, or if I do, it might be extra credit or something. Roughly speaking, my understanding is the following, that if you take the object and you condense it down to a single point, right, and you revolve it, let's say, around the x-axis like this, right? So if the object has the same mass, just concentrated at a single point, that this would be the radius at which you would have the same kinetic energy as the entire object rotating around the same axis. So it gives you the equivalent kinetic energy. The kinetic energy is, 1/2 mv squared, or in terms of a solid object rotating around an axis, it's 1/2 I omega squared, omega being the angular velocity. But again, that's that's physics, and we're not going to get into that here. Okay, so here's our example. We want to find m is the mass, x bar, y bar, that's the coordinates of the center of mass, ix, iy, I0, those are the moments of inertia, for the planar lamina r, which is the region in the xy plane, where y is between 0 and 4 minus x squared, so that's the usual upside down parabola, and x is between 0 and 2. Right? So that's this dark blue region here. Right? So this is r inside here. And again, here's the boundary of it in green. And the density is x squared times y. Right? So we just have to calculate all these integrals. And yes, that's a lot of them. I'm only going to do this one example because, you know, if you can do this, you could probably do the others as well. So let's start with the mass, and that's usually the first thing we have to calculate, even before you do the center of mass, right? The center of mass involves dividing by m, so let's calculate m first, right? So m, well, the formula for m is just the double integral over r of the density, right? Sorry, dA, don't forget dA. And, well, the region is essentially given to us. There's no reason, I think, to convert to polar coordinates here. Or if you want a real challenge, you could. I just don't see the point. I don't think it's necessary. This is not a, circular object. It doesn't have circular symmetry, right, or radial symmetry. But yeah, you could do it that way too. So this is the integral from, let's say, x equals 0 to x equals 2. And then the integral from y equals 0 to y equals 4 minus x squared. And then the density is just x squared times y. And dA, in this case, is dy dx because I'm using it. I'm thinking of this as a vertically simple region, right? Yeah, so we just have to evaluate this iterated integral. So we can take out the x squared and just do the y integral first. So integrate y dy. Right? So just do this integral. And you get 1/2 y squared as your antiderivative. So take out the 1/2. Yeah, so y squared evaluated between 0 and 4 minus x squared. We still have to integrate with respect to x, right? But what we're integrating is 4 minus x squared squared, right? Yeah, so if we expand that out, if we multiply that out, we get 16 minus 8x squared plus x to the 4th. And at this point, this is just a standard, standard single variable definite integral. So it shouldn't be that hard to work out. The integral is 16x minus 8 over 3 x cubed plus 1 over 5 x to the 5th. And we're evaluating that between x equals 0 and x equals 2. So at this point, I would just shove it all in a calculator. All right, so I get 1/2 of, so the thing in the brackets here is 256 over 15. Right, minus 0. When you plug in x equals 0, you just get 0, right? So divide by 2. This is 128 over 15. Right, or about 8.53. I want to save the space here. So again, let's just leave it as exact. 128 over 15, it's good enough, right? So that's the exact answer. That's the exact mass, right? And again, I'm not giving units here, so it could be kilograms, it could be, slugs, I don't know. It's just a number at this point, right? All right, so now we can do x bar and y bar, right? So to do x bar, we're going to take 1 over m times the double integral of x times the density. And 1 over m is really 15 over 128. It's the reciprocal, right? And then the region R is still from 0 to 2, and then from 0 to 4 minus x squared. Right, and then x times the density. Well, the density is x squared times y. So x times that is going to be x cubed times y. Right? And no, so I knew I was going to mess this up. Okay. Okay, I got to fix this. Okay, so back up a little bit here. I forgot the x squared. Right? So, yep, we had to multiply all of this by, x squared as well. So we multiplied it out okay, right? I got 16, yeah, here's the x squared, right? 16 minus 8x squared plus x to the fourth, x. But I forgot to multiply by the x squared. So, I'm going to do it all over again. This is going to be 16x squared minus 8x to the fourth plus x to the sixth dx. Right. So when we integrate all that, again, I'll leave the 1/2 outside, right? We're going to get 16 over 3 x cubed, right, minus 8 over 5 x to the 5 plus 1 over 7 x to the 7th. And that's going to be evaluated between 0 and 2. Okay, so again, I'll leave the 1/2 for later. So when you plug in 2, again, when you plug in 0, you get 0. So when you plug in 2, so you get 1024 over 105. So I think that's 512 over 105. At least I hope I did that right. Okay, so that means I also have to fix the constant here. The 1 over m is going to be 105 over 512. So that's an easy fix here. Hang on, 105 over 512. Okay, now I think we can proceed. Sorry about that. All right, so this is, yeah, and so this is x times the density, x cubed y, dy dx. All right. Right, and since the y comes first, we can pull the x cubed out and do it this way. Again, don't forget the, x cubed, not x squared. And I'll try not to forget it this time, but now we're just integrating y again, which is essentially the same thing we had earlier. So that part is going to be the same. 512, right? Sorry. 512. Yeah, so the outer integral is from 0 to 2 of x cubed, and then we have 1/2 y squared. Okay, so 1/2 y squared evaluated between 0 and 4 minus x squared. Right, and we still have to do the x integral. So you pull out the 1/2, and this is 105 over 1024. The integral from 0 to 2 of x cubed times 4 minus x squared squared. So that's still 16 minus 8x squared plus x to the fourth. And then when you multiply all that out, sorry I'm writing small, I hope this is not too small here. So we get 16x cubed minus 8x to the 5 plus x to the 7 with respect to x. So, When you integrate all those, your antiderivative will be 4x to the 4 minus 8 over 6, so 4 over 3 x to the 6 plus 1 over 8 x to the 8. Is that it? And then plug in 0 and 2 again. Yeah, the 124 incorporates the 1/2, so I can't forget about that. All right, so when you plug in 2, 32 over 3. Again, not 100%, but I think that makes sense. I mean, effectively, this is going to be 2 to the 6, right, minus 2 to the 2 times 2 to the 6, so that's 2 to the 8 over 3, plus 2 to the 5, right? So 32 plus 64 is 96, and then minus 128 over 3. Oh, wait a minute, minus 256 over 3. 2 to the 8. Yeah, 32 over 3. Okay. So that is 35 divided by 32. Yeah, 32 times 32, 1024. Okay, so 35 over 32. Again, very tedious calculation, right? All we did was the mass and the x coordinate of the center of mass. So this is x bar, remember? So we're only halfway through the center of mass. We also have to find y bar. So to do y bar, very similar, but still, you got to do it all over again, right? This is going to be y times the density. So 1 over m is still 105 over 512. And we're still integrating from 0 to 2 for x, and then from 0 to 4 minus x squared for y. But now sigma was what? Sigma was x squared y. So I think we get x squared times y squared dy dx, right? Right. So let's see, we integrate y squared and we get 1/3 y cubed. Don't forget the x squared again. That's good advice for me, right? So you're going to get x squared times 4 minus x squared cubed minus 0, right? Y 0 cubed is 0. Okay, so expanding all that out, and the 105 divided by 3 is still 35. So this is 35 over 512 so far. All right, so what's the integrand? Well, okay, I'm not going to do it all at once because I would probably mess it up. So x squared times what, right? 4 cubed is 64 minus, let's see, 3 times 4 is 12. Gosh, I'm trying to do this in my head, right? So let's see, you're going to get 4 squared times x squared times 3. So 16 times 3 is 48 x squared plus, and then I think we're going to get x to the 4th times 4 times 3, so that's 12x to the 4th, and then minus x to the 6. Does that make sense? Yeah, I think that's it. All right, so now just distribute the x squared. And you're going to get 64x squared minus 48x to the 4th plus 12x to the 6 minus x to the 8. That looks weird. X to the 8 times dx, right? And then your antiderivative will be 64 over 3 x cubed minus 48 over 5 x to the 5 plus 12 over 7 x to the 7 minus 1 over 9 x to the 9. And now we just plug in the 2 again. Okay. Again, that's for my calculator to do. And I get 8192 over 315. Again, I hope that's right. So now when you multiply that times 35 over 512, I get 16 over 9. And that's y bar. Yeah, so x bar is just a hair above 1, and y bar is close, not quite 2, right? 1.7 something, 1.78. But that's it, right? So again, in this object here, the center of mass will be just a little bit above 1 for x, and somewhere right here around the middle of the R, roughly, or maybe a little bit to the right here, right? So there's your center of mass. Okay. Great. So yeah, like I say, you can see how tedious these calculations are, but it's just more practice doing double integrals and iterated integrals. Not fun, right? And we're only half done. We got to do Ix, Iy, and I0. So Ix first. Ix is, so it's the double integral of y squared times the density. And again, the density is x squared y. So I think we're going, again, from 0 to 2, 0 to 4 minus x squared. Yes, so x squared times y cubed. Oh, yes, no, don't divide by the mass here, right? There's no 1 over m here. So this is it, right? This should give you the moment of inertia. And again, we can split this up because we can bring the, dA, yeah, so this is vertically simple, right? dy dx, sorry about that. So we can bring the x squared here, and then we do 0 to 4 minus x squared, the integral of that, y cubed dy. And so we get 1/4 y to the 4th now, right? So 4 minus x squared to the 4th dx. And at this point, look, we could multiply all this out. Why don't we just stick this in our calculator and see what comes out? Yeah, so this integral is going to be 262,144 over 3,465. Right, exactly, right? And so when you divide by 4, you get 65,536 over 3465, right? Which is approximately 18.91. Right. So here's the exact, here's the approximate. Right. And again, we didn't give units. What are the units of moment of inertia? Well, if we look at the definition, right, it's basically a density times an area, so that's a mass, times distance squared. So it could be kilogram meter squared, let's say. So this has units of mass times area. So kilogram meter squared. I think that's it. I'm just double checking. Yeah. Yep. But again, we're not worried about units here, right? All right, and so we also want the moment of inertia rotating around the y-axis. So remember, there you multiply by x squared times the density. So same integrals, same limits, but now it's x squared times y. So x to the fourth times y. X squared times y. X squared times y squared. Okay, I'm just checking the other one. Yeah, x squared times y times x squared is x to the fourth times y. dy dx, right? Now we still have to do the inside integral here, right? So 0 to 2, x to the fourth, and we're going to get 1/2 y squared evaluated between 0 and 4 minus x squared. So pull the 1/2 out in front, and we're going to integrate from 0 to 2, x to the fourth times 4 minus x squared squared. And this one's not quite as bad to work out by hand. All right, let's do it. So 1/2 times the integral from 0 to 2. So x to the fourth times x to the fourth is x to the 8. Minus 8x squared times x to the fourth, so 8x to the 6. Plus 16x to the fourth. Okay, so that's the integral we have to evaluate. And again, this is one that I think you can just do right on your calculators. We're not in Calc 1 anymore, right? You've done this many, many times. So I'm assuming that this is not an issue. So if you want to just use your calculator or computer, go right ahead. So this time, I get 4,096 over 315. And yeah, when you cut that in half, I think you just get 2,024. No, sorry, 2,048 divided by 315. 350, right? And that's approximately 6.5. 6.50, good enough. I think that's it. So again, units are kilograms times meters squared, but let's not worry about that. All right, I think that's it. Oh, I0, the polar moment of inertia. So we still have to do I0, right? But here's a nice shortcut, right? If you did Ix and Iy, you can split these up as two separate integrals, right? Let's do the y squared first, although it doesn't matter. Right? It's the sum rule for integrals. It works for double integrals too. So I0, the polar moment of inertia, is just Ix plus Iy. Right? So for the approximate, we just have to do 18.91 plus 6.50. And that's going to be 25.41. I should never do this in my head. 25.41, right? I mean, that's the approximate, but that's, at this point, I'm pretty happy with that. Again, if you want the exact value, well, then you're just going to do these two fractions here. So you're welcome to do that, but it is approximately 25.41. So yeah, to get the polar moment of inertia, all you have to do is add the Ix plus Iy, the sum of the two moments of inertia about the x-axis and y-axis. Okay, so I think I don't know about you, but I'm pretty exhausted from doing all that, at least mentally exhausted. It's very tedious, right? A lot of these problems in this section are going to be just as tedious, and so shortcuts. Basically, once you're down to a single integral, right, a regular definite integral, you're welcome to just plug that in your calculator or computer, right? What I don't want you to do is just plug this in your computer, right? You do have to work out the first integral here. Once you're down to a single integral, a regular definite integral from Calc 1 or Calc 2, that you can just use your calculator for. But your calculator is not going to give you a double integral, or if it does, then you're not allowed to use it. So yeah, you can plug this in Mathematica or MATLAB or Maple or pick your favorite software, right? Or your favorite app. I've been using Wolfram Alpha to do these single integrals. But unfortunately, it will do double integrals as well. But yeah, but don't, right? I mean, spend a few minutes working on it. Don't go directly from here to here. I will, right? That's not enough work. I will say, you didn't show your work. So show your work, right? But if you didn't spend the time working out, right, this integral here, that you're welcome to use your calculator for, obviously. All right, so hopefully that's right. That should do it for this section. Again, right, all you have to find is the mass, center of mass, and moments of inertia. Don't bother with the radius of gyration. They could ask for that, but I'm not going to ask that. So you can either skip it or do it for fun. Right. In fact, it's not much more work here. You just use the formulas. So already having calculated the y moment of inertia, you just divide by m and take the square root. Not a big deal. But yeah, took up the whole screen for me to do just this one example. And right, I don't see the point in doing another example. And you're going to maybe do 2 or 3 of these, but in most cases, it's hopefully the math will be a little bit simpler. Or at least the algebra and the arithmetic will be simpler. And read the question carefully. In some questions, I don't actually want you to work this all out, right? In some questions, the question might just say, write down the integral, or write the integral, the double integral, right, for the x moment of inertia, Ix, right? But do not evaluate. Right? In other words, you don't have to bother with all this arithmetic here, right? So what am I looking for Ix, for example? I'm looking for this double integral, this iterated integral here. I don't mean this, right? That's just a formula. Right, you have to actually express that double integral as an iterated integral, right? And then that's it. You don't have to bother evaluating it. If it says do not evaluate, then right. So yeah, I want you to figure out how to write down the iterated integral, and then from there, you just do the calculation, right? In other words, you can plug this into a calculator or computer, and it'll spit out the answer. Right. But there will be at least maybe 1 or 2 problems where you do have to work out all this stuff here. In other words, you do have to evaluate the integral, right? So, but that's Calc 1. That should be second nature to you by now. And don't worry about making little arithmetic mistakes here and there, right? So yeah, you'll lose a point or 2. But if you have the right idea, if you have the correct formula, right, and you mess up, you lose a point or 2. It's not a big deal. But if you get the wrong integral, like let's say you use x to the 4th instead of x cubed, then you're missing a concept here. You're doing x squared instead of x or something like that. So just write down the correct integral. But then if you mess up the evaluation, you're not going to lose that much credit for that. But if you write down the wrong integral, you could. Especially if the whole question is just to write the integral, and you write down the wrong integral, then you're going to lose a lot of points for that, because that's all I have to go on here. All right, that should do it. I hope this helps.